Okay, how's everybody today? Okay, well, we finally made it. This is our last lesson of the year. Tomorrow, the seniors will be gone. You guys have, I believe, is it a 10 a.m. meeting? Okay. So you won't be on campus, but you'll still be here. Won't be in the classroom. For the rest of us, I'm just going to give you the class period to work on your review if you've not already had the opportunity to take a look at it. How many people have looked at the review? Okay, so you'll have some time tomorrow to go ahead and do so. Then Thursday will be your final, and that is it. It'll be the last time I see you folks. Any questions? Yeah? Okay, well, let's see how far we can get with polar equations. Yesterday, I started talking to you about circles, and I introduced limesons, and I brought up roses a little bit. But let's just do a quick recap. Like circles, for example, they were in the form a cosine theta or a sine of theta, and where they were with respect to the pole depended on the sign of your scale factor. So, for example, cosine was either to the left or right of the pole, because if your equation only has cosine, what kind of symmetry can we expect to see? There were three types we looked at yesterday. Horizontal, what do we call that? With what axis? With the flat one. Starts with a P. Polar, the polar axis. There you go. That means I should be able to fold it horizontally. The two parts are going to come together perfectly. Okay. For sine, the circle was either above or below, again, depending on A being positive or negative. But what kind of symmetry am I going to see in the graph if it only contains sine? Okay, so that was theta equals what, Jack? Theta equals pi over 2. There we go. So I could fold it vertically, and the two sides are going to coincide perfectly. And then there was one other form of symmetry that we were looking at with respect to the... What's that? One more time. Well, it could be diagonally. It's if you rotated it 180 degrees, rotational symmetry. So that was with respect to the pole. There we go. That's exactly right. Now, one of the first things we did yesterday was we performed tests on different equations to go ahead and see what kind of symmetry they had. We did so by either replacing the radius with its opposite, we replaced theta with its opposite, or we replaced both the radius and theta with their opposites. If I want to go ahead and perform a test to see if it's symmetric with the polar axis, which of those three do I perform? Stephanie. If it's with the polar axis, algebraically, would I replace the radius with its opposite, theta with its opposite, or both the radius and theta with their opposites? Just theta. If I can replace theta with its opposite, simplify, and get the original equation, it should have symmetry with the polar axis. Okay. Well, what do I do if I'm looking for symmetry with theta equals pi over 2? So there's only two left this time. Do I replace only the radius or the radius and theta? Brett, what do you think? Okay, if I replace both the radius and theta with their opposites, if it simplifies to the same equation, then it's going to have symmetry with theta equals pi over 2. Now, if I want to go ahead and show symmetry with respect to the pole, 180 degree rotational symmetry, then all I have to do is replace the radius with its opposite. Okay, and then we moved on to limesons. Now, we didn't get very far. Basically, I went ahead and showed you the form, either A plus or minus B cosine theta or A plus or minus B sine theta. And you'll note this is different from a circle in that that expression for a circle is now being added or subtracted from a numerical value. You'll notice still, whether it's a circle or a limeson, the coefficient of theta is still 1. Okay, it can't be anything besides 1 or else it becomes a completely different type of graph. So let's begin there. Let's see. We worked through these examples together. Here are a few more. So let's say I gave you 4 minus 3 cosine theta. Okay. What's the value of A? A is 4. What's B? That's absolutely right. When you're identifying A and B to figure out what type of limacin you have, you always take those values as positive, even if B is being subtracted. A and B are always going to be positive. Well, we have 4 different types of limacins here. We have an inner loop, a cardioid, that's your heart-shaped graph, a dimpled limacin, where just one part of the circle has kind of been poked in, and a convex limacin, where one part of the circle flattens out. Okay, so let's see. Which of the 4 is it? When I compare A and B, which one am I looking at? Okay, what's that, Christian? Which of those 4 would this one be? Inner loop, cardioid, dimpled, or convex? Okay, he thinks dimpled. Let's take a look. So first I want to show B is less than A. So 3 is less than 4, which is good so far, which is also less than 2B. 6. So is that a true statement? Absolutely. So that would be a dimpled limacin. Okay, perfect. Perfect, good. What if I were to give you that next one? 2 minus 2 sine of theta. That's a cardioid. This is the case where A equals B. Okay, and what about this last one right here? Negative 5 sine of theta. Is that a limacin? Why not? There's no value of A, so this is a what? What was the type we were just looking at? It's a circle. There you go. Now, where would the circle be with respect to the pole? Let me go ahead and draw my axes here. Pole, where they intersect. It's going to be vertical because sine is symmetric with pi over 2. Okay. It'd be below because the 5 is what? Negative. Okay. And that length right there would end up being 5. Okay, good, good, good. Now, this little section prior to this, where it says practice finding the maximum and minimum values of R, I'm not going to go ahead and worry about that because we're about to graph one, so I'm just going to go ahead and show you how we do it. I'm going to show you the strategy. Okay, so let's graph our first limacin. Now, just like with circles, there's a couple of steps that you want to go ahead and follow to make things a lot easier on yourself. Okay. Hello. Hey, thank you. Okay. Dylan. There you go, sir. All right. Okay, so just like with circles. Oh, what is it? You know, I really need to start looking at last names too. I just saw Dylan. Let me see if I can catch him. Sir? Wrong classroom. Yes, sir. I don't have a student by that name here. Should have looked at the last name. I'll be careful.
Wait, it's 2204, right?
2204, yeah, but I don't have a student by that name. Thank you, sir. Okay. Sorry about that, Dylan. Okay. What was the last name, Dylan? I didn't even look. Rios, there you go. I do that same thing in other classes, like in 8th period. I have 2 Josephs. And even at the end of the year, I still haven't gotten to where I should look at the last name. I just do Joseph and go to the closest one. So I feel bad. But then I get over it. Anyways, like when you were talking about circles, we wanted to go ahead and set the equation equal to 0. And then we wanted to go ahead and set the trig function equal to plus or minus 1. Well, when you're dealing with a limacin, there's 2 steps here that are going to be very useful to you. Replace the trig function with plus or minus 1. That is how you determine the length of the maximum radius and the length of the minimum radius. Okay? And then step number 2, set the equation equal to those values you found. Okay? So by the time you finish up 2 steps, you should already have 2 points on your graph. Okay? So first off, let's go ahead and see what kind of limacin would this be. Looks like A is 1 and B is 3. So if I come back over here, which one does it satisfy? This is going to be a limacin with an inner loop. Okay. Okay, so let's see if that's exactly what we get. So replace the trig function with plus or minus 1. So the radius equals 1 minus 3 times 1. Or the radius equals 1 minus 3 times negative 1. Okay. And remember, this goes back to the maximum and minimum of the parent graph. This is why we're doing that. This is going to help me find the maximum radius and the minimum radius. Well, what's 1 minus 3 times 1? Negative 2. Is it okay for the radius to be negative? What happens if the radius is negative? Yeah, remember, you just find that direction in the exact opposite direction. What about 1 minus 3 times negative 1? 4. So the radius is 4. So the larger of the two is 4. So that has to be my maximum length in the graph. Negative 2 would have to be the minimum radius length. Okay. So that's step 1. That's all I got to do. In fact, that is what we would have done on that previous section. Okay. Now, step 2, I'm going to go back to the original equation, and I'm going to set it equal to these values that I found. So, for example, 1 minus 3 cosine of theta, I'm going to set it equal to negative 2. And then I'm going to do the same thing with this. 1 minus 3 cosine of theta equals 4. Why am I doing this? What's this going to give me? The value of cosine? There you go. Because see, I have the radius measures. This is going to help me find where they occur, the theta measure. Okay, so it's just like any other equation. How would I solve 1 minus 3 cosine theta equals negative 2? Okay, so subtract the 1. So negative 3 cosine theta, negative 2 minus 1, negative 3. Divide by negative 3. Cosine theta equals 1. Now, what do I got to do to cosine? Got to take the inverse. There we go. So cosine inverse of 1 is going to give me theta. So let's think back. We mentioned this previously. I don't remember if we mentioned it yesterday or if it was last week. What two quadrants will cosine inverse be restricted to? It's 1 and, not 4, 1 and 2. 1 and 2. So think about the top half of your unit circle. All the ordered pairs that are there. I'm looking for the one ordered pair that has an x value of 1. What is that? It's just 0. It's a quadrantal. Okay. So I now know that the shortest length of the radius ought to be 2. Remember, the negative just tells you direction, and it should occur at 0 radians. So see, that gives me an ordered pair. I can go ahead and say negative 2, 0. And you'll notice I did mine in radians. If you want to do yours in degrees, makes no difference. Okay. And now let's go ahead and find out where the maximum radius occurs. So I'm going to start by subtracting 1 again. Negative 3 cosine theta equals what? 3. Divide by negative 3 cosine theta equals negative 1. And just like before, we have to take the inverse. So cosine inverse of negative 1 is going to give me theta. Well, where in the upper half of the unit circle do I have an x value that's negative 1? Pi. There you go. Okay. So now my ordered pair, when the radius is 4, that occurs at pi radians. Or if you want to say 4, 180, perfectly fine. Okay, completely up to you. Now you'll notice I went ahead, because the only trig function you have is cosine, what kind of symmetry should I be seeing? With respect to the polar axis, or theta equals pi over 2? The polar axis. So you'll notice I only used theta measures from the top half of the unit circle, because I knew that I could reflect it across the polar axis. Okay. In fact, if you go ahead and take a look, you'll notice negative 2, 0, and 4 pi, those already appear on my table. That's why I always like to go ahead and use ordered pairs that go with the symmetry. I just kind of think it makes it easier. All right. So now I've already got that filled in for you, but where did I get those values from? Like, where did I get the negative 1.6 here for the radius? What did I plug in? Yeah, I just plugged it into the original equation. So 1 minus 3 times the cosine of pi over 6, that's where I got a negative 1.6. Now, remember what mode your calculator is in. You'll probably want to go ahead and change it to degrees, or if you want to change your mode to radians, I would probably just convert to degrees. Okay. But let's go ahead and plot these points. before I do, any questions? Is anybody not sure how I found anything? Okay, well, let's see here. My first point is 0, -2, so it's 0 radians. I'm going to go in the opposite direction, so I'm going to start with this point right here. Then we have pi over 6. That's a 6 right there. What was that, -1.6? So pi over 6, and maybe a little past halfway. Then we have pi over 4, -1.1. So that'd be right there past -1. And pi over 3, -1/2. Okay, so we're talking probably about like right here. Okay. All right. And then we got pi over 2, 1. And then we got 2 pi over 3, 2.5, 1, 2.5. 3 pi over 4, 3.1, 1, 2, 3.1, so that's going to be just past it. And 5 pi over 6 is 3.6, so a little past halfway. And my final point would be 4 pi. Okay. So this gives me exactly half of the points I would need in order to finish it up. So all I did was just plot those points, what we did the majority of our time last week. Any questions on that? Okay. Well, now how am I going to complete the graph? I'm just going to reflect those points. Let's start with the ones below the x-axis, the ones that'll be the inner loop. So I'm going to have one here, one here, one here. Okay. Then I'll go ahead and reflect the others. So I should have one right about here, maybe one here, and then we'll have one right here. Hello. There's no Dylan Rios here. No. Okay. There were 4 people bringing that pass. They're looking for Dylan Rios. Maybe it's a good thing. All right, and then all we got to do is just go ahead and draw your curve through the points. What I like to do is go ahead and start with a point, and I go ahead and just draw the whole thing without lifting my pencil off the paper. Okay. Jack, you're impressed by that? Slightly. Well, then be ready to be impressed. So I'm going to start here at the pole. I'm going to go the inner loop, outer loop. Jack, you weren't watching. There you go. There's our first limacin. Okay. All right. And if you don't want to go ahead and draw like in one motion like I do, I mean, you can go ahead and just do it in 2 separate. I mean, it's still going to be the same graph. It's completely up to you. Okay. Any questions? Anybody's not sure where we got anything from? What's that, sir?
What?
Oh, no, the sign on your chest.
Oh.
Stephanie's daddy?
Yeah, it was for a play. It was for a play.
Okay.
And also, it's Stefan. It's a dude.
Oh, Stefan. Oh.
Yeah,
Stefan's daddy.
yeah, because it's French.
Ah, oui. Okay. Okay. All right, moving on. Let's try one on our own. That's something that caught my eye. All right, so you're probably saying, Mr. West, you know, this is the last lesson of the year. I want to try one on my own. Well, all right, I'm going to go ahead and deliver. We're going to graph this one, 6 minus 2 sine of theta. So let's identify what it is first. What's A? A is 6, B is 2. So if I come back over here, okay, well, it's definitely not another inner loop. Is it a cardioid? Not a cardioid, okay. So let's check dimpled. So B is 2, 6, which is less than, what's twice B? 4, is that a true statement? Nope, so it has to be convex. All right, so A was 6, which is greater than or equal to twice B. We should end up with a convex graph. One side of the circle is going to be flattened. Okay, now all I'm interested in right now is simply you completing the first two steps. Okay, find me the maximum and the minimum lengths of the radius. Then use those lengths to find where they occur, the theta value. So go ahead and get me those two polar coordinates. Now, if you feel really confident, create your table, go ahead and graph it. Okay. But while you guys are doing that, I'm going to pass back papers. For walls. For walls. For walls.
Can I go to the next real quick? Get offended.
Yeah. Let me get you a pass. Oops. Bless you. Oops. Yeah. Okay. Here today is. Thank you, sir. Mm-hmm. The great Gillen. Thanks. You can. It doesn't go far off, or you can count it by twos and it'll fit nicely. Say one more time. Let's finish up this problem. Oh, sorry. Okay, that's all the papers. While you guys are finishing up, I'm going to take advantage and get the roll done. Okay. Now, you may not be done, and that's okay. So can anybody tell me what are the two lengths, the max and minimum radius we should be getting? 4 and 8. There we go. That's exactly right. Replacing sine with a +1 and a -1. Okay. Gives me 4 and 8. Then I'm going to take those values and I'm going to plug them back into the equation. Okay. So 6 minus 2 sine theta equals 4. 6 minus 2 sine theta equals 8. And what are the theta measures I should be getting? Pi over 2 and negative pi over 2. There we go. Remember, sine inverse is restricted to quadrants 1 and 4. Okay. So again, because of where I was restricted and the theta values I got, I decided to go ahead and use the right side of the unit circle. But is there really anything saying that I couldn't have gone pi over 2 all the way to 3 pi over 2? Would that have still given me the graph? Yeah, absolutely. I mean, I just like to try and make it a little easier on myself. Any questions on how I got these two polar coordinates? How many people got that right? Okay, that's good. That's good. That's actually more than any other class so far. Very good. So now I'm going to take that, and it's just time to go ahead and fill in my table. Okay. So these values, we know that at pi over 2, I should have a 4. Negative pi over 2, we have the 8. And now we just need to go all the way through. So I need 6 minus 2 sine of negative pi over 3. Let's just go ahead and round to 1 decimal place. Erica, can you help me out with that one? If I were to plug negative pi over 3 into here. Now, what is pi over 3 in degrees? Negative 60. So I could say 6 minus 2 sine of negative 60. 7.7. Perfect. 7.7. Okay, now negative pi over 4. Miriam, can you help me out with that one? So 6 minus 2 sine of negative 45 degrees. $7.4. Good. Now I need 6 minus 2 sine of negative 30. Brenda, can you help me out with that one? 7. Okay. Savion, can you help me out with 0? Zero. So 6 minus 2 sine of 0. 6. Okay, pi over 6. Fours. Help me out with that. 6 minus 2 sine of pi over 6. 5. Okay, 2 to go. Susie. Pi over 4, 45 degrees. Got 4.6. And Ford, why don't you finish that up for me? Pi over 3. Or 60 degrees. 4.3. Perfect. There we go. Now, Aiden asked me this question while I was passing out some papers. You'll notice the largest radius you have is 8, which goes off the graph. It doesn't go off by much, but you could simply just count the rings by 2s. So the innermost circle, we could say 2, 4, 6, 8, and so on. Okay. So this is the final opportunity during a lesson to come up to the board. Who would like to plot these points for me? Final opportunity. There's going to be people going home today. Oh, I should have gone and done it. I have the students' regret. But who will not go home and say that tonight?
I will.
Jack? All right. There you go, sir. Okay. Or we can count by 2s. No? Okay. So then I would just go ahead and estimate it. So like 7 might be right about here. So about 8 probably right about here. Okay. And then if 7 is going to be maybe right about here, then maybe 7.7 right about there.
Yeah, but it would be here because
Oh, you're right. You're right. Sorry. Seeing if you were paying attention. Oh, we're going a little more. That would probably be about 7.
Oh, so like here?
Yeah, maybe. We need it to be closer to 8.
Like half of this is off the graph. Maybe
Well, I know. That's why.
Like
There we go. That'll make it easier. So negative pi over 2, 8. There you go. So 7 would be halfway. So I'd say about 3/4 of that would be 7.7. Okay. Negative pi over 4, 7.4.
it's not putting it where I want it to go.
Okay. Whoa, whoa.
It's hell.
Oh my gosh. What?
It won't go where I want it to. Like the dot keeps going like a little bit off.
How did you do that?
I have no idea. But it's all up. It's
Yeah.
all up.
That was interesting. Okay, let me get rid of that. Yeah, get over there. Okay.
Man, this is a struggle. I have mad respect for the people who come up here. Come on, please.
Okay.
0, 6, right?
Yeah.
Yep.
Mhm. And then pi over 6, 5.
Oh wait, too low.
Okay. Okay. Thank you, Jack.
All of them are really off, so.
No,
On a bad note.
we get your point. Perfect. 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 Okay. Okay. Now I'm just going to go ahead and reflect those. Now you'll notice, where is the side that's going to flatten out? Yeah, it's the top. I mean, you can just take a look at the values. I mean, how close they are to each other. So let's see if I can match up his. There should be one right about here, here. Then we got to go here. Okay. Then we're going to go 2 up and a little over 2 out, maybe about right here. Then right here. Then right there. Okay. Would you guys say I reflected his points pretty well? Okay. And now we just go ahead and draw our graph. Okay. I kind of missed those points over there. Imagine I hit those points in there. That's it. That's my convex limacin. Did anybody happen to go all the way on that problem? Actually, because I only asked you to do the first 2 steps, create the table and actually sketch it. So a few people did. Good, good, good. Okay. All right. Well, the only thing left, I want to talk to you very quickly about roses. And as I said yesterday, we do not have enough time to go ahead and do one of these by hand. This is one I did by hand last year because we had way more time. You'll notice there's a little more involved when it comes to plotting these, especially the more petals you have, the more points you're going to get. Okay, but I'm just going to go ahead and show you a much easier way just for the sake of time. Let's say I give you these 2 right here. 5 sine of 3 theta, 5 cosine of 4 theta. So we already kind of mentioned it, but how do I know at first glance these aren't circles? What's the difference? There you go. It's not 1 theta. We have some coefficient other than 1. That's what differentiates a circle from a rose. So take a look at 5 sine 3 theta. What would be the length of each petal? 5. So the coefficient of the trig function is going to be how long the petal is. How many petals would I have? Okay, so 5 sine of 3 theta, you say would have 3 petals. What about 5 cosine of 4 theta? Now, what's the difference? There you go. If it's an odd coefficient, you keep that number of petals. If it's an even coefficient, you double that for the number of petals. Okay? So I'm going to show you how to put this in the calculator, which I did not show my students last year. Okay? So you should feel special. They do. Okay, let's go. All right. So what you're going to do is go to your graphing screen. You're going to go to menu. You want graph entry edit, and there's polar. So you'll notice you can type in your polar equation here. It only does it within one revolution. Okay, positive. Theta steps, 0.13. So I just gave you 5, what was it, sine of 3 theta? Now here's the thing. If you're typing in a polar equation, you have to plug in theta. If you use x like you normally would with a graph, it's not going to give you anything. It's not going to identify it. So there's a lot of ways to get theta. I come down here to this pi button. Okay. Plug in theta. If I go ahead and push enter, there's my rows. Each petal is 5 units long, just like we talked about, and there's 3 of them. Okay. Let me show you the other one. Tab. Go back up. We wanted 5 cosine this time. It was a 4 theta. So there you go. There are the 8 petals. And you'll notice, think about the symmetry. 5 sine of 3 theta had symmetry with pi over 2 because it was sine. This one actually has symmetry with both. Okay. And it actually doesn't have rotational symmetry. Jack is absolutely right. This one is symmetric about the pole as well. Okay, very good. Does anybody want to play with this real fast? Like put in a crazy number of petals? 143? That's such a weird number. Okay. The highest that any class has gone so far has been 1,000. Okay. So let's. So here's 143. Kind of looks like a sea urchin. What if you do a decimal? I don't know. Like what kind of decimal were you thinking? 5.5? I honestly don't know. Oh, the petals overlap. Looks like 2 of them are only half as well. That's pretty. Okay. So tab. So let's try, I think, Raphael, you said 1007? There you go. And, you know, if you can go ahead and get some pretty cool graphs with smaller numbers as well. If I were to do something like, you know, maybe 20, you'll still be able to see all 40 of those. Okay. So it just gets to a point where the resolution isn't able to distinguish between the petals anymore, and it looks like a blob. Okay. But even the graphs that we did today, if I go to document B, now how did I get to the polar graphs? Menu, graph entry edit, polar. And the inner loop one, I think it was 1 minus 3 cosine theta. Is that right? So 1 minus 3 cosine of theta. So there's the inner loop that we graph by hand. Okay. You can look at circles. You can start looking at other types of roses. Basically, there you go. Okay. All right. And unless anybody has any questions, that is it. The final lesson of the year. Okay. Let's shut her down.